So integrals have this practical meaning that they are the area under the curve. It's the area between the function and the x-axis. So that's what we're going to talk about in this lesson. And it is a little bit more abstract and complex than most of our lessons. And if you're completely new to the idea of integrals, you might want to think about watching this several times, not back to back. Just kind of let it wash over you the first time through. Return to it maybe after doing some problems. This is kind of the heart of this unit on integrals that, as I was saying in the last lesson, are extremely important for things that you as social scientists need to learn, but a little bit hard to wrap your brain around. Okay, so what we're going to be talking about here is, first of all, we're going to be just talking about the problem of calculating the area under curvy lines. That's geometrically more difficult than calculating, say, the area of a rectangle, but the way we do it in calculus is based on approximating the area with rectangles. Okay, so we're going to talk about that. Then we're going to talk about taking limits. That's how we do things in calculus. When there's something we don't want to do, we find a way to get as close as possible to it and use limits to think about that. So we're going to think about the integral as the limit of a sum. I'll say more about that when we get there. And then we're going to try and tie these ideas together. Why does the process that gives us the reverse of the derivative, that undoes the process of differentiation, why does that also give us the area? Okay, so that's a lot. Throughout this, what I'm trying to help you do is get used to thinking about integrals in three different but nonetheless related ways. Okay, that integrals are antiderivatives, like we said in the last lesson. They are the area under a curve. That's what I'm asserting now. And that they are also the limit of a sum. Sometimes you'll hear this expressed as a continuous sum. So all three of these ideas are kind of coming together in this lesson. So let's get on with it. And I imported some of the pictures from the notes because I'm not going to trust my bad art here. So in this first panel here, here's kind of the problem that we're interested in. We've got this function, it's not linear, and what we want is to find the area that is underneath the function. Okay, so the top is defined by the function f of x, and it's between, in this case, 0 and x bar. So something that I'm going to note here is that area is itself a function of x. So kind of notice the similarities to slopes and derivatives. Something that we can calculate easily for things involving straight lines. It gets harder when the curves are curvy. Also something that is itself a function of x. That's what I was sort of drawing in here. Although once we put in a number for x bar, then we can put a number on that function. We can evaluate that function at any value of x we want. And that was the same with the slope. The derivative is a function, but once we plug in a value for x, it's a number. Okay. So we want to find that area, and we don't have the nice kind of geometric formula that, say, we have for a rectangle for something that's curvy. But we do know how to calculate the area of rectangles, right? So thinking about a way to maybe approximate the area under this curve here is we could divide up the area that we're thinking about and dividing it up into 4 pieces along the x-axis. And as we'll see, that number is going to change. We divide it up into the 4 equal parts, and then we could calculate the values of each of these rectangles, and we'd get a total area that would be smaller than the area under the curve. We've got this white space here that's showing area that we're not counting here, but it would still be an approximation. Okay, so that's sort of what's going on in this final panel here. I've given each of those rectangles a name, L1, L2, and L3, and let's just add up the areas of those rectangles. So when I'm saying adding up the rectangles, that's sort of shorthand for adding up the areas that we can calculate. Okay, so area of a rectangle. Let's just remind ourselves, what is that? That is height times width, okay? And I'm gonna, as we do in calculus, I'm gonna call these intervals on the x-axis, I'm gonna call each of them delta x. Okay, so what I've done is divide up the area I'm trying to find, 4 areas. So each delta x here would be x bar over 4. That doesn't matter so much, but just each of these rectangles has a width of delta x and a height that depends on x. Okay, so just looking at this area here, those 3 rectangles, the area of L1 is, so what I'm doing here in finding the height of the rectangle is I'm doing the height at the lower value. So my delta x here would be x2 minus x1. And so the width is delta x. Okay, that's my width here. For the height, I am finding the function evaluated at the lower limit. Okay, so f of x1. That's a parenthesis. Okay. So again, let's just be really clear here. What I have here is height times width of the rectangle. And for L2, same width here. It's x3 minus x2, but it's still delta x. I set it up so that all my delta x's would be the same because let's try to simplify things when we can. Okay, so delta x is the width, but now my height here is, what is it? Oh, it's the function evaluated at x2. Fine. x2. So again, each time I'm evaluating the height of the rectangle at the lower of the x values. And that is indeed what these L's stand for. What we are working on right here is calculating a lower sum. That's what this is called. Okay, so you get the picture here, the area of the third rectangle. It's still got a width of delta x, but now the height here is the function evaluated at x3. Go up here, what's the functional value? That's what it is. x3. And just sort of preview some stuff we're going to see in a minute, I could even write this as a sum. I could say this is the sum as I goes from 1 to 3 of f evaluated at x sub I, okay, times delta x. This is my lower sum, this sum of the 3 rectangles. And the thing to bear in mind as we're going to go on to the next slide is that the lower sum understates the true area that we're looking for here. We're looking for all this gray area. The lower sum is getting some of it, but it's leaving out this, it's leaving out this, it's leaving out that. Okay, so it's going to use an estimate, but the estimate is too small. Well, we could do it the other way, right? We don't have to evaluate the function at the lower x value. We could do it at the higher x value. And guess what? That's called an upper sum if we do that. So same deal. We're looking for the true area. We've divided the interval up into exactly the same number of parts, exactly the same delta x here. But now, instead of evaluating my rectangles at the lower limit, it's not permanent marker here, at this limit, and at this value, and this value. Now what we're doing is for each rectangle, we're evaluating it at the upper limit. Okay, so we've now got 4 rectangles. You might be thinking, how come we have 4? No, we had 3 before. We actually did have 4 before, but remember when we were evaluating the height of the rectangle at the lower limit, the first height was 0. So that's why that one rectangle just went away. So here we have the upper sum where in each case the width of the rectangle is delta x. So 1, 2, 3, 4. Each of those has width of delta x. But now the heights are the height of the function at the higher x value here. Same for this, same for this, and same for this. So let's write that. Okay, so the upper sum is the function evaluated at x1, the higher of the two heights for the first rectangle times the width, plus f of x2 times that same width. Okay, so again, it's for the second rectangle, the higher of the two heights, plus the function evaluated at x3, delta x, plus the function evaluated at x4 times delta x. And again, we could write that as the sum as I goes from 1 to 4 of the function evaluated at the ith x value, the ith upper value, we would say, times delta x. Don't want to turn my delta into a d just yet. So write it the way you're supposed to, Kathy. There we go, delta x. Delta x is the width of all of those rectangles. Okay, so we've got 2 ways of approximating the area that we're interested in. The lower sum gave us an area that was too small. We had that white space. Here, the upper sum is giving us an area that's a little too big. Okay, this doesn't really belong to the area we're interested in. This is also an over assessment. All of these are places where the upper sum overstates the true area. Okay, so stepping back, what can we do to make these approximate areas closer to the true value? Well, if you just kind of look at the picture, it's pretty easy to see that if we let those rectangles get skinnier and skinnier, and so then we'll have more and more of them, we're going to get closer to the true area. So here I've got simpler pictures with still a lower sum here that's, you know, understating the area, and upper sum that's overstating the area, giving us too much here. But we're actually getting closer. And this is, you know, now you see why this is a part of calculus. Again, what do we do in calculus when we can't quite calculate something? We go to the limit. So what we're going to think about now is let delta x go to 0. Okay, let's have the base of those rectangles get vanishingly small. And what is going to happen is that both the lower sum and the upper sum will approach the true value. So let's write that. I stumbled a little bit saying it, but we have the lower sum here. The area of the lower sum was the sum as I goes from 1 to n of the function evaluated at the lower value. So I'm writing that now as x to the I minus 1. So it would be the f0 height would be the first one. That would be our 0. And then we would have the, I guess there's 7 rectangles there times delta x. And the upper sum here is similarly sum as I goes from 1 to n. X sub I, upper sum now. So we've got this I here. We're taking the upper x value and multiplying by delta x. Okay, so now let's take limits. Okay, the limit as delta x goes to 0. So one thing that happens is these two things get closer and closer together. The limit, they're approaching the true area from from above and from below there. And once we take the limits, that's where the sums turn into the integral sign. So I may not have mentioned in the last lesson, the whole idea behind this curvy shape for the integral sign is supposed to look like an elongated S. Okay, it's supposed to remind us that this is in fact a sum of things that are becoming so small that they're just kind of blurring together so that we can't even see any space between the things. The sum, so we have the sums, we take the limit of the, as delta x is going to 0, the summations, the capital Greek letter sigma, become these elongated s's, and we have the integral of f of x. And our deltas become d's, just like they do with derivatives. Okay, so this is the integral is the limit of the sum. Okay, stepping out of our narrative for a minute, one reason why I'm kind of belaboring writing out these summations at every point is next quarter when we're using integrals in probability, the most important thing, yeah, probably is the most important thing that I want you guys to be able to do is not calculate those integrals, but when you see an integral with a bunch of stuff after it, to recognize it as, oh, is this a probability? Is this an expected value? Is this a variance? And you'll be better able to pick it apart if you can look at those integrals and say, what kind of sum does that look like? Okay, that's so this limit of a sum point is important and useful for being able to read arguments that talk about integrals. Okay. All right, so the last thing we need to do is address this why question. Why is it that the process that gives us the antiderivative also gives us the area under the curve? To me, that's like not at all an obvious thing. So that's what's going on here. Why does the antiderivative give the area? Okay. All right, so let's kind of just sort of step back and assess what we have here. We now have this idea that the area is a function of x, okay? And that the area is related to the height of the function. That's sort of like once you start thinking of the functional value as the height of some rectangle and a set of rectangles whose bases are getting infinitely small, it makes sense that the area should be influenced by the nature of that function. Okay, and so the claim here that in saying that the antiderivative gives the area, what I'm really saying here is the derivative of area. Yeah, it's doing. With respect to x is the height. That's what it means. We were saying that the area is the integral. The derivative of the integral is the original function. That's what this basic statement is. The whole thing that we're trying to explain. Okay, and I've got it kind of illustrated here in the pictures with the blue. So we're thinking about the change in area here. And again, we're thinking about this as a discrete change, and we're going to let delta x go to 0. So before we let delta x go to 0, let's think about delta x not being 0. And so we've gone, our gray area goes up to x, and then we're just adding delta x more here with the blue. Okay. So as x increases from x to x plus delta x, the area increases by delta A. This is the true over here in the first panel. We've got the true change in area there, where the top of the blue area is defined by the function itself. And just as when we're calculating the whole area, we can approximate that change in the area with both a lower sum that's going to be a little too low. It's going to leave out this area because it's going to use the original x value for the height. And we've got the upper sum here that's going to give us a little too much area because it's using the x plus delta x value to give the height. Okay. But just as we argued before, I'm going to say that the true delta area, okay, my delta A here that is from this panel, the true value is bigger than the lower sum, okay? So it's bigger than f of x times delta x. So that's the lower sum here has a height of f of x and a width of delta x. But the true area is less than the upper sum, and that also has a width of delta x, but now the height is f of x plus delta x. Okay, so we've gone delta x further on the x-axis, and the function has gone up a little bit further. Okay, so the change in area is in between the function evaluated at the starting point times delta x and the function evaluated at the ending point times delta x. Okay. So that x plus delta x, that should look familiar, right? We did that same thing. We wrote our ending value that way when we were taking limits of difference quotients to get to derivatives. Okay. So we set ourselves up to take derivatives that way. Actually, I want to do one thing before I take limits here. We're still in this world where delta x is not 0, so it means we can divide through by it. So I'm just going to divide through each element of this inequality. When there's inequalities, we always want to be asking ourselves, are we sure it's positive? Yes, we're setting it up so it is positive. It's a positive discrete change in x. So dividing through by delta x, it goes away here. We get a, look at that. We get a difference quotient in the middle. That's looking good. And here on the end, it divides out there. So we're left with, okay, now I'm ready to take limits. Okay. So the limit as delta x goes to 0, x is less than equal to the limit as delta x goes to 0 of delta a over delta x, and that is less than or equal to the limit as delta x goes to 0 of x plus delta x. I'm not quite sure why I switched colors here. It's kind of building up to the most important thing, so I guess I wanted to highlight that. Okay, so let's have yet another color. Let's have purple be our color after we take those limits. Well, right here in the middle, this is what we're looking for here, right? This is the derivative of a with respect to x, right? The limit of the difference quotient, the limit of rise over run for a as a function of x is going to be dA dx. Okay, and that's cool because that is something that we're trying to make a point about. All right, what about over here? The limit as delta x goes to 0 of f of x. Well, f of x doesn't have any delta x in it. So it's just going to be what it is. The limit as delta x goes to 0 is not affecting f of x. Okay, so that just stays the way it is. And what do we have over here? As delta x goes to 0, x stays the same, delta x goes to 0. Well, look what we have here. This is also f of x. Okay, that's where the rabbit goes in the hat here. As delta x is going to 0, this is going to f of x. And that's, that is what we would see happening with this area here. This rectangle, that the blue rectangle, it's the change in area here, is just going to get narrower and narrower and narrower, because as delta x goes to 0, the x plus delta x is going to x. All right, that's all we need. The only way that both these things can be true, the only way that the derivative of a with respect to x can be both less than or equal to f of x and greater than or equal to f of x, that's on the greater than side here, is if it's equal. Okay, so this is only possible if dA dx equals f of x. That's what we're trying to find. Okay, so that is the idea. That is why the function that gives the height is the derivative of the area. And so those are two of kind of our three important ways of thinking about integrals. They're directly linked here, but the middle idea, the idea of the integral as the limit of a sum, which is how we connected the antiderivative to the area function, that is also really important, really useful, and is going to help you going forward. All right, so as I said, this is one of the mathier lessons of all of Math Camp, and it might be worth sort of multiple visits, maybe over the fall. We're going to go on to the next lesson right now, come back down a little closer to Earth, and do some actual calculations of area. So the hard theoretical abstract part of this unit was in this lesson. It is the most important. The more computational, concrete, easy to come up with problems to solve parts are in the previous lesson and the next lesson. And those are important only insofar as they help you understand this important stuff in the middle. So I'll see you in lesson 7C.